All right, how's it going, everybody? We are here on Tuesday of week 9. This is our first video of the week here for week 9. We'll get our second video tomorrow on Wednesday. This week we're going to be covering sections 9.3, 9.4, and 9.5. We hit 9.1 and 9.2 last week. And so we're gonna do these a smidge out of order here. If you're looking at what you see on the screen right here, part of the reason for that is you should notice that we went directly from chapter 7 to chapter 9. We are going to go and hit chapter 8 right after we finish up chapter 9 here. In chapter 8 that we have so far skipped, they introduce a new distribution that they then use in chapter 9, and they talk about using it in section 9.3. I'm still going to hold off on discussing that new distribution for as long as I can because I want us to get a good conceptual idea for what a hypothesis test is before we go and discover that there are lots and lots and lots of different versions of them. The big idea is that they're all essentially the same, just the computation changes associated with which distribution we are following. And so I want us to get a good, like, kind of core idea of just the hypothesis test today. And then tomorrow we'll go back and talk section 9.3, which will talk to us about the different distributions that are associated with hypothesis testing. Just at the beginning here, we're actually going to end up with a whole bunch of these over the course of the rest of the semester, but there are 3 different hypothesis tests we should be able to do by the end of this chapter. We're just talking about one of them today. We'll talk about the 2 sort of alternate versions, the two other scenarios in which we can perform hypothesis tests that are discussed in 9.3 in the next video. And several of the sections coming up here for the rest of this class are all discussing alternate versions of hypothesis tests. So this is very much a topic that's going to stick with us for the rest of the semester here. This is, in a sense, I don't want to say like this is the goal of the class is to talk about this, but this is probably one of the most important things of this class, hypothesis testing. We're going to do a lot of it. So this won't be going away here. So that's why it really matters that we get a good kind of a firm base here of what we're supposed to be able to understand about hypothesis test today, which is why I'm trimming this down to just one possible distributions hypothesis test. We'll get our alternate forms and some more examples tomorrow. So let's go ahead and get into this. We're basically just going to walk through 2 examples today, but we're going to do them very slowly, methodically, write out every single bit of information and only look at one possible distribution that's associated with the tests. Tomorrow, we'll maybe do them a little bit quicker, look through some more examples, look at other possible distributions that are going to alter our calculations slightly, but aren't going to alter at all our general structure and setup, right? So make sure that you're not paying too close attention to the details here and that you're kind of stepping back and seeing the big picture on this because the big picture will not change for the like 8 different hypothesis tests we'll do this semester. The fine details of the computation will change, but the big picture will not change from what we're going to set up here today. So, lastly, before I get started, I just want to remind you where we're at with our hypothesis testing. What we said several times now is that performing a hypothesis test is essentially a numerical or statistical method of applying the scientific method to an experiment. We need to form hypotheses, which is what we discussed in the last video. We'll form hypotheses for every single significant or hypothesis test that we ever do. Sorry, these are also called significance tests sometimes, hypothesis tests, those are the same thing. So we're always going to start by forming a hypothesis. We're always going to need to perform an experiment or collect data, which in our setting, in our classroom setting, that's always kind of done for us. We're always presented with, oh, a study was performed and 84 people were sampled and blah, blah, blah. Typically the case that data has been collected for us. Step 3, we want to analyze the data. That's going to be a big one that we're going to talk about today. And step 4, we're going to want to draw conclusions and make decisions, which you can see as being part of the section title here for 9.4. So those 4 main steps are what our general goal is with every hypothesis test. Form hypotheses, perform an experiment and collect data, analyze the data, use the analysis of the data to form a decision and make a conclusion out there. 4 main steps. So let's go ahead and see these. I'm going to break this down into more than 4 steps today, but it's just to make sure that we're seeing all the things that we need to see here. So we're going to basically talk section, section 9.4 and 9.5 today. Then we'll come back tomorrow and we'll get 9.3 and some 9.5 tomorrow. 9.5 is just our full examples out there that we'll see, and we'll get a couple of those today. What we still need to discuss is this idea of what constitutes a rare event, and how do we form a decision about our hypotheses based on the rarity of that event. So we're going to look at two examples here today. The first one will be a scenario concerning average human body temperature. The second one will be concerned with time to run a mile. And we'll discuss if we see any changes in the alleged averages associated with these things here. So let's go ahead and look at scenario one. And by the way, we will certainly be scrolling away from the screen right here. So I'm going to try and keep my two scenarios in the corner up there so you can always kind of re-reference the scenario that we're working on here. Also notice I've got an Excel spreadsheet set up down here in the corner. So I'm going to use this to track my data and to perform my computations that we've got here. So let's read through the scenario and let's ask these introductory three questions right here. So in this scenario, we're saying it is well known, and I'm putting that in quotes right there, that the average human body temperature is 98.6 degrees with a standard deviation of 0.65 degrees, and that's all measured in Fahrenheit. And when I say it's well known, what I mean is this is like a typical thing. If you ask a random person on the street, this is probably a temperature that they're going to tell you. For those of you that are old enough like me, then you'll remember that slightly less popular than Backstreet Boys and NSYNC in the 90s, I'd say the third most popular boy band was called 98.6 degrees. That's general common knowledge right there that 98.6 degrees is average human body temperature. So let's suppose that a researcher believes that average human body temperature is actually lower than that. And so the researcher decides she wants to test this claim. She's going to take a simple random sample from 33 people, and she's going to find that their average body temperature is 98.45 degrees. Right? So let's ask a couple questions about this scenario. First question we're asking here, is the sample average lower than the proposed population average? And here, our sample average, we've got our sample average. So really carefully, we're really going to lay out all the pieces here today to make really sure that we all see the parts that are going on here. Remember, our sample average is always given as X bar. That is the average of the sample that was taken. And in this case, our X bar was 98.45. Here, our population average, the claimed population average was the 98.6. This is always going to be denoted by mu right there, 98.6. And so the answer to our question here is yes, it looks like our sample average was below the population average. So the question that we want to ask is, does this show that average human body temperature is lower than 98.6? And here, the very important thing to understand is that the answer here is no. We always expect variability in our samples. Come on, that doesn't make any sense. Why would you erase that? So the point is, it is unclear if this difference we see is due to variability of the sample or a real difference. Right? So like technically I drew a sample that was different than what we expected from the population average, but that kind of thing happens all the time, right? If you go out and you collect a sample of 15 people and measure their average height, it's incredibly unlikely that you're going to find their average height to be exactly the population's average height. It's likely that you're going to see something that's a little bit off from it, but probably pretty close to it. There's variability in every single sample that we take. So the thing that we don't want to go do here is say, oh yeah, 98.45 is less than 98.6, so she was right. We don't know that. This could have just been a perfectly normal, lightly varied sample right here. Or maybe this represents an extreme departure from our average of 98.6 that we're thinking is actually correct here. It's not really clear to me which of those is true until I do a little bit of computation to see how unlikely really is it. So our next question here, how can we attempt to prove that this data does suggest that average human body temperature is lower than 98.6? And our answer is, let's determine exactly how likely this is. Let's determine the probability of sampling 33 people and finding an average temperature of 98.45 given that the true average is 98.6. So here's the very, very, very important underlying thing that's happening. Um, Listen to this statement very carefully here. This is a really important part of every hypothesis test that we're ever doing. We are not looking to see what is the probability of getting a 98.45 as a standalone statement right there. What we're doing is we are assuming that our 98.6 is correct. We don't know if it is or not, but we need something to work from. We need a place, a jumping off point here. So we're saying, okay, let's assume that 98.6 is correct. If it were correct, what would be the probability of us seeing a 98.45 as our sample average across 33 people? What we might end up finding is that 98.45 is a totally typical event. Maybe we're going to find that it occurs something like 20% of the time, even if the true average is 98.6. Then we're going to say, oh yeah, it happens 20% of the time, even with that being the true average. It's pretty not unusual at all for us to have seen that outcome. Therefore, we don't really have any evidence against 98.6 being the true average body temperature. On the other hand, what we might end up finding is if we assume that 98.6 degrees is the true correct temperature, what we might end up finding is that getting a sample of 33 people that has 98.45 as their average temperature, maybe we find that that is incredibly rare, like a 0.01% chance of occurring if 98.6 were correct. Then we have to say to ourselves, either we happen to get the very unlikely sample that had a 0.01% chance of occurring, or 98.6 isn't right. In this case, if we get a sample that's super, super, super rare, like a 0.01% of the time it occurs, then that's going to lead me to say, listen, man, this thing is so rare, this sample that we got, if the 98.6 is right, that I no longer think the 98.6 is right, because look at how unusual this sample would be if that were correct. I'm maybe more inclined to think that the 98.6 is wrong and that my sample is probably not that unusual. Right? We want to decide between these two possible cases right here. So a very important thing for all hypothesis tests, and I know we haven't stated our actual hypotheses yet. Our hypotheses, our null hypothesis will be that 98.6 is true average body temperature. It's our statement of no change. We will always do all of our calculations with hypothesis tests, assuming that the null hypothesis is true. If that leads us to a crazy place, then we will go back and say, you know what, our results were so crazy, I don't actually think the null hypothesis is true anymore. That's what will allow us to change our mind about some of the parameters that we're interested in identifying here. So let's go ahead and identify a whole bunch of things here. We would like to determine how rare it would be to sample 33 people and get an average of 98.45 under the assumption that 98.6 is truly correct. So in this case, I want to identify a bunch of parts and then we'll do some computation here. So first things first, tell me what population parameters we have been given that are associated with this scenario. Remember that population parameters are always describing the entire population. Population parameters have nothing to do with the sample that was drawn. So here the population parameters that we have been given are the population average, which is 98.6, and we've been given a population standard deviation of 0.65. All the other numbers in here, 33, 98.45, those deal with what the sample collected. Those don't have to deal with the population as a whole. So our our population parameters here, population average, population standard deviation. Those two things were given. I am asking these questions, by the way, in a slightly strange order. Notice that I'm looking for the population parameters, then the hypothesis, then the sample statistics. The sample statistics are sort of the partners of the population parameters. But very importantly, when you are performing the scientific method, you always will state your hypotheses before you perform your experiment. It's very bad science to go collect a bunch of data, then form a hypothesis and test it. We want to kind of have an unbiased view of the things that we're maybe or maybe not going to see. So it matters that we always state hypotheses first. So that's just why I'm trying to put our little blurb about hypotheses before I state our blurb about what happened to the sample. It's always the case in good science that a sample is collected after a hypothesis is formed. So I'm just trying to keep sort of chronological order of our real world scenario in place here. So our hypotheses, we decided last class that we're always going to have a null and an alternative hypothesis. We said that our null hypothesis is always our statement of no change. It's always going to be our statement that includes an equal to symbol. Our alternative hypothesis, we said, is always going to be the hypothesis that we're suspicious might be true. It will always include greater thans, less thans, or not equal tos. In this case here, we are trying to make a statement about the population average. We're always making statements about population parameters. The parameter being considered here is the population average. That's the thing that we're testing for. We're not sure if the population average is correct, so that's the thing we're making statements about in our hypotheses. Here then, my null hypothesis is my statement of no change. It's the statement with the equal sign. It's the statement that says, yeah, no change would be, yeah, we're going to stick with the idea that average body temperature is 98.6 degrees. What are we suspicious is actually true, though? This researcher is suspicious. It says right here, this researcher is suspicious, believes that average human body temperature is lower than that. So that's going to lead me to say my alternative hypothesis that I actually kind of think might be true is that our average body temperature is actually below the 98.6 degrees right there. All right. So in general, by the way, over here, we will refer to mu sub 0 as 98.6. This is like saying, according to the null hypothesis, mu is 98.6. But remember, the entire point of this entire process, and almost the entire point of this class in general, is for us to argue that maybe those things aren't true. How do we ever update our information, right? How do we take in data to update what we think that we know? And so here I'm just trying to really say, the whole point of this experiment is we're actually a little bit unclear about what the true population's average body temperature actually is. So I'm just kind of distinguishing this by saying, well, according to the null hypothesis, true average body temperature is 98.6 degrees. But we're kind of arguing maybe against that here. So I don't want to keep on making statements that sound like true average body temperature is 98.6. We might find that that's not true here at the end, right? So I'm just trying to say, if I ever put a subscript of 0 on one of our population parameters, that's just me saying that's what the null hypothesis claims is the truth. So we've got our two hypotheses here, and ultimately the long-form goal of this is for us to make a decision that says we either think that the null hypothesis is true, or that we get evidence that says that the null hypothesis is false, meaning that we're going to go with the alternative hypothesis that would say that we are less than 98.6. So we want to set up these hypotheses because the ultimate goal here is for us to choose between the two, but we want to let the data and the statistics choose between the two for us here. So just as we have stated our sample statistics here, or our population parameters about the whole population, we should also state the statistics that are associated with the sample. So again, looking at my scenario over here, I can see that I do have a sample size of 33, and I did get a sample average, the average of the sample, X bar, to be 98.45 degrees. Okay. So what we're going to want to do here, and if you're looking at the top of my screen, is we want to determine how rare it would be to see a sample like this. That's really saying find the probability of seeing a sample like this. Well, I know that I can't compute a probability of any event unless I know what distribution the samples follow, right? So what we need to know about the distribution of our variable of interest here. So we were originally given the X distribution. We were told that X is normally distributed. Ooh, okay. So that's maybe a typo, my bad on my part. Let's make sure that we acknowledge this is um, that these blood temperatures, that these body temperatures are normally distributed right here. Yeah, so my phrasing right here, I should have said, it is well known that average human body temperature is normally distributed with an average of 98.6 and a standard deviation of 0.65. I will be, so some of these technicalities are going to matter. We're going to talk a little bit more about those technicalities tomorrow here. Right, so we're assuming in our scenario that we are normal here. So we're normal. We've been told 98.6 is our average. We've been told that 0.65 is our standard deviation. But what we're more interested in here is our distribution of the sample means. We're not interested in the probability that one person has a certain body temperature. We're interested in the probability that a group of 33 people on average have a certain body temperature. We want to know how groups are distributed, not individuals. So our sampling distribution for the sample mean then should be normal. And by the way, in this guy right here, I certainly didn't say that our individuals for X were normal right here, but what we can find is that because 33 is larger than 30, the central limit theorem will tell us that even if this our individual was not normally distributed, our groupings of 30 or more will be normally distributed. Their average value will be normally distributed. So in this case here, we don't even need this information. This is what we need to be normal. And the thing that we know it's normal because of is because our sample size here was larger than 30. So when we take groups of more than 30 at a time, the distribution of their averages will be normal. This is the distribution of the averages right here. So our average is going to remain the same. It's still going to be 98.6. We're just taking bigger groups at a time. But here we're going to see our standard error term, the new standard deviation term, is going to be quite a bit smaller because it's going to be our old standard deviation divided by the square root of n. And by the way, let's give a name to this. This is our standard error. What's going to happen here, as I kind of was alluding to at the beginning of this video, is that we're going to see a bunch of different hypothesis tests crop up this semester. And the only thing that's really going to change is where we get these two numbers from. All the rest of this process is going to be essentially the same. These two numbers are going to end up getting computed differently, which will lead us to do different computations for like our normal distribution stuff in Excel or our TI calculators. But this is really the one thing that's going to change. We're just going to basically be getting new computations for standard errors based on new types of scenarios. So this is like the one thing that we expect to be the thing that changes over time. So what I'm now interested in computing is a test statistic. I finally need to actually do some computation here. So I'm going to step over, by the way, into Excel right now and show you how I'm kind of organizing my information. I'm going to scroll up a little bit so we can see all the numbers that we've discussed so far on the screen here. So what I'm going to do is I'm just going to build a list that's tracking all the data that we've seen so far for this problem. So I'm just going to mark this as number one. And in number one, what we've seen is we're first given mu. That was 98.6. We were then given sigma. That was 0.65. We were given the sample size, n. That's 33. We were given the sample average, that's x bar. That's 98.45. And the reason that I'm doing it this way is because I know that I'm going to use some of these values to make some computations now. For example, I know that a term I'm going to need in a moment is I need to know what that standard error term actually is, right? 0.65 divided by the square root of 33. Let's just go ahead and compute that in Excel over here. I'm going to just call this standard error. And this should be my standard deviation, the 0.65. I'm seeing that as cell C5 right here. That's my standard deviation term. I want to divide that by the square root of cell C6. That's my number of samples right there. So I want cell C5 divided by the square root of cell C6, according to the way I've got my Excel stuff spread out here. So I'm going to say equals C5, you can see it highlights the sigma term, divided by square root, I can just do SQRT in parentheses, divided by the square root of C6. That's my n term right there. And it's going to give us our new standard error term, Looks like about 0.113. We can see that it's much smaller than the 0.65 that it originally was because it's much harder for groups of 33 to deviate from the average than it is for just one person to deviate from the average. So we've laid out all of our our data that's associated with this problem here. Um, so now what we want to do is compute the probability of seeing an event that looks like this. So what I'm thinking to myself is I want to know how many standard deviations away from normal is our sample. Assuming the null hypothesis is true, how many standard deviations from average was our sample? I'm going to write this out by hand. I am also going to compute this in Excel over here. So what we had first seen this semester is we first saw that we compute z-scores as x minus mu over sigma. But this is for individuals. We are now talking about entire samples that we want to compute a standard deviation, a number of standard deviation for. So we're still going to form something that's exactly of this structure right here. We just need to upgrade what our actual terms of interest are. We're no longer collecting just one single x. We're now collecting an entire x bar, an entire average from a group of people. So we're going to get x bar minus mu. We're going to say how far was our sample average from the population average. And now, instead of just dividing by the standard deviation of one observation, we're going to divide by our new standard error term that we got right here. And by the way, I guess I should just write this as 98.6, comma, 0.11315, right? So I've computed this number over here in Excel. I can see what we've got right there. So I'm going to write this here as, I'm just going to write this as sigma over root n. I'm going to write this in general here. This should be our 98.45 minus 98.6, all divided by our 0.11315. And I'm going to go ahead, I'm going to do this again over here in Excel. I'm going to come over here and I'm going to say, well, I can compute my z-score now. I have all the information associated with my z-score. So it should be, notice again, all the parts I need are listed in Excel right here. I've got my 98.45, that's cell C7, minus cell C4, that's my mu, all divided by cell C8. That's my standard error term right there. So I can use my list of information here to compute the next values of interest. So I'm going to do equals. I want x bar minus mu, so that's C7 x bar minus compute my z-score, and this is telling me that it looks like we're getting about 1.3 standard deviations below normal. So we've computed what we will call now our test statistic. It's called a test statistic because it's associated with our hypothesis test here. This is our computation of saying if the null hypothesis were true, then the sample that we drew is this many standard deviations from average. And what you should notice is that this is not too wildly far from average right here, right? We typically think of things that are within 2 standard deviations of average as being typical results. That is very much a hand wavy and finger quoting a statement right there. But still, to see 1.3 standard deviations from average, it's not too weird. It's not very strange to me. What I still want to know, though, is I don't want to just try and make these like vague judgments. I really want to know what really is the probability that we see something at least as extreme as this guy right here. So what I'm kind of picturing to myself is that we're out here on our bell curve, right? We know that our sampling distribution of the sample mean, our x bar distribution, is normal. It should be centered, and I'm just going to give some I'm going to list this as my z-axis here instead of my x-axis. So what I want to know is what's the probability of seeing events that are this unusual, right? What's the probability that I would perform this experiment again and see a result at least as extreme as the one that we just saw? Notice here, this 1.3 puts us right about here. This is at my test statistic location right here. This is my z equals 1.326, or negative right there, negative 1.326, right? That is the location of our sample that we drew. Our 33 people landed here on our sampling distribution, 1.3 standard deviations below normal. All of this area out here then represents the probability that if we were to perform this experiment a second time, that we would see an outcome at least as likely as this one right here, at least as unlikely, I guess I should say. These are all the events that are at least as extreme. So extreme is always going to be towards the tails, away from the average right there. So what is the probability that we see an event at least this extreme or more? Well, by the way, real quick, let me scroll up real quickly here. We had originally stated that our alternative hypothesis was that we only believed our only other option was that we were going to get less than 98.6. And so what that resulted in is us only shading the left tail associated with our normal distribution over here. So what we now want to go ahead and compute is what we are going to come to call our p-value. And man, oh man, our p-value's super freaking important here. If you want to get a bunch of nerds all worked up, go shout some crazy things about p-values to them, and they will all lose their minds. There's a very, very large amount of debate as to the importance, validity, and use of p-values in the statistics community. They are certainly useful, but there are plenty of situations in which people abuse p-values, which we're going to talk about quite a bit in the next coming weeks here. So just kind of know that our p-values are wildly important. Our p-value literally just represents this area that we're looking at over here. This is our p-value. It's our probability of seeing at least as extreme of an event if we were to perform this experiment again. In this case, we can compute our p-value just by doing our typical normal distribution computations here. I can see that I have a standard normal distribution centered at 0, standard deviation of 1. I know my z-score that I am interested in probability to the left of, right? So this should be a relatively easy normal distribution calculation for us to perform here. So let's go over here and compute our p-value associated with this sample that we've drawn. So I'm going to compute my p-value, by the way, two different ways, just to make sure that everybody's on board with these two alternate techniques for doing this here. One thing I can do is I can use my z information to compute my p-value. In this case, I'm going to do norm.s.dist because I want to do my standard normal distribution. That's exactly the graph that you're seeing right here. In this case, it only wants from me a z value, which I have as negative 1 point. Actually, what am I doing? I don't need to type that in. That's cell C9. C9 is exactly my z value. Notice I don't have to do any rounding this way now. That is the z value of interest, and I'm always going to have to tell it true for cumulative here. Excel always gives me area to the left. Area to the left is what I want right here, so I don't have to do any like 1 minusing to flip it. And I do this, and there's my p-value right there. So we're going to talk about interpreting that in 1 second. I just want to show you that we could also do this using our x information. Right? This would just be a regular old norm.dist, not a norm.s.dist, because we're not standard normal. I'm now going to just use this information from my distribution of the sample means there. X bar is normal 98.6.11315. I'm going to use this information alternatively as my alternate form to throw this information in here. So back over to Excel here, norm.dist. It wants from me my x value. That's my sample item right there. So that's my 98.45. Oh wait, I don't need to be typing in any of these. That's my C7. That's my 98.45. Next up, it wants my mean. That's mu. That's C4. Next, it wants my standard deviation. That's sigma. That's C5. And finally, it wants to know if we're cumulative or not. And yes, we are. And so when we do this, oh wait, what the heck? What did I do? What did I type in wrong here? C7, C4, C5, X. what? Norm.dist C7. Oh, I'm using sigma instead of my standard error right there. That was done. I'm using my standalone sigma 0.65 rather than the 0.65 divided by um, r square root of n. So when I said C5 here, instead of doing sigma, it should have been my standard error. That should have been CH right there, our standard deviation divided by the square root of n. And notice when we do this, we're getting the exact same answer right there for that p-value. So it looks like here we have computed our p-value. And I'm going to say this is our probability that z is less than negative 1.326. Also the same thing as the probability that x bar was less than 98.45, and we found that this was 0.0925. So how do we interpret this? This is really important for us right here. Remember that this is a probability. The p-value is a probability. So let's type some things out here. The p-value is the probability that if we were to do that if we were to perform this experiment again, collect a sample, collect a body temps from 33 people and average them, that we'd see an average at least as extreme the one we just saw. All right, so let me just stop right there and say a few things. So our p-value is saying, listen, if we were to do this whole dang thing again, perform the whole experiment a second time, what's the probability that we'd get another sample that's at least as extreme as the one that we just saw? This is like saying, what's the probability of seeing a sample that's extreme under the null hypothesis? Assuming the null hypothesis is true, how unusual was this sample? Here, our p-value, 0.0925, says that we have a 9.25% chance of seeing samples this extreme, assuming the null hypothesis is true. And what I want to sort of conclude here, softly, this is my soft conclusion, what I want to softly conclude here is that this is not that weird. Getting an event, seeing an observation that is likely to occur almost 10% of the time is not a very normal situation. This is a pretty typical type of result right here. This is not that weird. All right, so what do we want to conclude from this then? If this isn't that weird, what does that say to us? Well, we want to form a conclusion now, right? I mean, now is our kind of final statement right here, which is to say, Claire, super good question. So our question in chat right now is, would that be the same with the same sample size, or 9.2, or would 9.25% chance be with any sample size? Now, here's the thing that we want to see here, Claire, with what you just said right there. And I'm going to show you some things in Excel right here. So here's the thing to know. What did our sample size do to us computationally? What our sample size did to us computationally is it's sitting right there. There's our square root of n. It's down there in our standard error term. And so what we want to see is that our standard error term here will get smaller and smaller and smaller as n gets bigger and bigger and bigger. That means it's harder and harder for our groups to deviate. So watch what happens here as I change my n value relative to my p value. So one thing we might say is, well, what if we sampled many fewer people? What if you actually only took a sample of like 10 people and got that 98.45? Well, with 10 people, I'm way less convinced that that's anything strange at all, because that's just a 10-person sample. So I expect that to be a pretty typical type of sample to experience. I expect my p-value to get larger if I make my sample smaller here. So notice if I make my sample only 10, then now we're saying, yeah, this occurs 23% of the time. That's not that unusual at all to get 10 people, because it's easy for 10 people to deviate from average. On the other hand, so what did we start with? We started with 33. Well, what if we did 10 times that many people? If we did 330 people that were sampled and got that 98.45, what I've got to think to myself is 330 is kind of a lot of people. If we sample that many people, it's very unlikely that they're all going to deviate from the average in one direction or the other. So I feel like it's super difficult for us to end up in a scenario where we sample 330 people and are like wrong, really, right? So notice here, now when I do my 330 person sample, notice that this is saying that this is more than 4 standard deviations away from average now. It's a very unusual sample to draw relative to the null hypothesis here. We're really sitting kind of middle of the road on this one. So this number, by the way, down there, that's like our 0.0000138. So that's a really tiny probability down there. That's like a 0.00138% chance that we would sample 330 people and get this average when this was really the true correct average right there, right? So Claire, one thing, super good question that you're asking. You should exactly be asking these types of questions. How does this change when we change the standard deviation? How does this change when we change the sample size? How does this change when we change the sample average? Stuff like that. And the reason why I'm going to encourage you, gosh, I got to flip my camera. I'm going to say this forever. The reason I'm encouraging you to do this in Excel in a table like this is because it's super easy for you to just play around with the numbers and see how things end up changing out there without really having to do any sort of work, as long as these are all linked to each other's cells in there. So I would very strongly encourage you to do that, so you can sort of just play around and be like, what happens if it goes to 33, 34, 35, 36? And we can just kind of do those things here, right? 34, 35. I notice, now I'm making mistakes right there. Notice if we're watching our z-score get larger and larger and larger as our sample size gets larger and larger, because the larger our sample is, the more confidence that we should have that that's actually the correct thing that's going on there. And therefore, that's a more and more unusual sample that we should end up seeing right there. Notice that even by the time we're at 37, we're now down to this just being an 8% occurrence instead of a 9.25% occurrence, because with 4 more people in our sample, 37 instead of 33, we should have a little bit more confidence that our sample is correct relative to the null hypothesized mu value there. So, and we're going to play that same game again with our next one coming up here. So we'll do that Excel game again right there. So ultimately what we kind of want to conclude here is that the sample average that we drew from 33 people was not that unusual relative to the null hypothesis average of 98.6 degrees. Therefore, we don't have sufficient evidence to reject the null hypothesis, right? We would want to see a much more rare event for us to believe that the null hypothesis was false. So we want to talk 2 things right now. 1, I want to repeat some statements from before. 2, I want to introduce kind of the last piece of this that we haven't seen yet, that hopefully is like the question that you're asking in your head right now. Get out of here, grammar. Stop checking much more rarer event. No. So here's the deal. I'm kind of just pulling this answer out of nowhere right now, which is what our big issue is. What we need is a better decider for this, so that you know exactly what decision to make. Again, I want to repeat some statements from earlier. We are now trying to choose between, let me just type this. We are choosing between 2 truths. One of them is the null hypothesis is correct. U equals 98.6. So always we are choosing between two possible truths when we are making our conclusion. One possible conclusion will always be that the null hypothesis is correct and that our sample was just maybe a little weird. And that can happen. That's called probability and statistics right there. There's always going to be variation. The alternate conclusion that we could be drawing is that our sample was unusual enough that we no longer believe that the null hypothesis could be true, right? If we were to get a super rare event, if we got a p-value that was tiny, 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 then that would say there's an incredibly small probability of pulling that type of sample, assuming the null hypothesis is true. But what are you really going to believe? That we just pulled like a 1 in a million sample the one time we pull a sample and that's just what happens? That's probably pretty unlikely if we do get a p-value that small. It's probably more likely that our null hypothesis was wrong to start with, and that's why we computed such a small potential value for that p-value. And by the way, again, this is not a very small p-value. This is like a 9.25% chance of this type of thing occurring. That's not that weird, right? So here, I'm going to say 9.25% is not weird enough for us to believe this. Our data supports this statement. All right, so we've got these two different statements here that we're always trying to decide between. Every hypothesis test ever, you're going to be essentially deciding between the null hypothesis is correct or our sample is so unusual that we think that the null hypothesis can't be correct, right? That we no longer believe that the null hypothesis could be true. We're always trying to decide, is the null hypothesis true or not based on what we just saw? But what our issue is here is that we need to decide how weird is weird enough. That's really our last kind of item here. And so the last thing I want to define here for us to be able to get through all of our hypothesis testing here is the idea of a level of significance, which we are going to denote with the Greek letter alpha. An alpha level is typically given before, at the introduction of any hypothesis test, because what this is going to say is it's going to say to us, how crazy of an event do we need to see for us to draw that line in the sand right here, right? I'm going to say here, typically, alpha is given in the problem. Most typical value for alpha is 0.05. This says we need to see an event at least as rarely as 5% of the time or less for us to decide to reject the null hypothesis. And here's the issue with alpha values. I said a minute ago that people get all up in arms about misuse of p-values. People are about 5 times more upset about improper use of alpha values here. But again, we're going to talk about a bunch of these things. We just kind of want to get our base established right here. So typically we'll go into experiments saying, listen, for example, this is like a cancer drug trial. We need to be pretty dang sure that this drug actually works. And so we need to make sure that when we perform the trials for this drug before it goes on the market, we need to be seeing events that, if our null hypothesis that the drug has no effect, we want to be very certain that the drug does have an effect before we go distributing it to people and letting people think that it's going to help them out with their cancer, right? So in medical situations, it's often the case that we see very, very, very small alpha values, right? If we see an alpha value of like 0.01, then what that says is that we need to see events that are less likely to occur than even a 1% chance relative to the null hypothesis for us to claim that there was truly an impact from those drugs right there. That's a very difficult threshold to get over. So what this alpha is measuring here is this is like your weirdness threshold. Right? This is saying, how weird does my sample need to be for me to cross the line and say, you know what, I'm rejecting the null hypothesis, right? So this is an unusualness measure. This is like a line that we're crossing out there, right? If we find our p-value is less than our alpha value, then our likelihood of our sample was more extreme than that of the proposed limit set by alpha, and therefore we will reject the null hypothesis. We see our alpha, or our p-value, to be smaller than alpha, then our sample was more extreme than our weirdness cutoff of alpha. Okay, so alpha is basically our line in the sand that we're drawing of saying, was that extreme enough or was that not too extreme? Most typical alpha value to see is 0.05. In this case, we got 0.0925 saying ours was a little bit weird, but it didn't cross the line of weirdness. The weirdness line here was 5%. We got a 9.25% probability of our sample. That's not so unusual. If we would have seen a sample that, for example, would have only occurred like 4% of the time, then maybe that would be extreme enough for us to say, you know what, I kind of think the null hypothesis is false here. I'm seeing strong evidence that the true population average is actually less than that. And again, coming back over to Excel over here, we can screw with these numbers a little bit. If I'm looking for a p-value of less than 0.05, saying it's past this threshold of a 5% event weirdness, then maybe, we bump our sample size up to 40. That's still not quite enough. We've still got a p-value of 0.07. Maybe if I go all the way to 50, ooh, 50 is getting really close here. 50, I still am seeing that this type of sample would occur more than 5% of the time, 5.1% of the time. But it looks like we could maybe go to like 52, and it looks like we've now dropped past that alpha value threshold. So if I had given you this problem with all of everything the exact same, except the n value was changed from 33 to 52, then I would be making the opposite conclusion here. Because in this case here, seeing 52 people be sampled and seeing a sample average that looks like this gives me more confidence that this is truly correct because our sample size got larger. It's harder and harder for bigger and bigger groups to deviate from the true average. So I might be inclined to say, if all else the same, if n was changed from 33 to 52, I might be inclined to say, you know what, I kind of think that body temperature actually is less than 98.6. But with our 33 in here, our probability of seeing an event like that under the null hypothesis being true is a 9.25% chance. That's not that unusual. It's not that weird. And so we're going to say, this isn't enough evidence for me to throw out the null hypothesis, right? So, so So first things first, in stating our conclusions, I'm always going to state my level of significance. This is saying, how weird did I need to see things to make my decision? Otherwise, it's not clear why I made the decision I made. So at the alpha equals 0.05 level of significance, our data were not significant, right? We did see a difference, but it was not a statistically significant difference with a p-value of 0.0925. So we failed to reject the null hypothesis. And finally, we conclude, if we're not rejecting the null hypothesis, then what we're saying is we don't have enough evidence to say that average body temperature is in fact less than 98.6. All right, so what I'm saying here, significant, is that we compared our p-value to our alpha value. All right, so here's kind of our decision-making rule. We want to always compute this probability that we get from the tail of our distribution. A lot of writing in there. We're going to trim these down a lot. Our p-value is always the area in our distribution. If our p-value is underneath our cutoff, right? If we were more extreme than our cutoff of our alpha value, then that's enough evidence for us to reject that null hypothesis. Our sample was too weird for us to continue believing that the null is true. On the other hand, what we just saw in our scenario here was that our p-value of 0.0925 was larger than a general alpha value of 0.05. And so we failed to reject the null. We didn't have enough evidence in this case to truly say it looks like average body temperatures are in fact lower than 98.6. Our sample that we collected is going to occur almost 10% of the time under the null hypothesis. That's just not that weird, right? That's just within variation of our variables out there. That stuff kind of happens, right? So here's our kind of final conclusion. We're going to make lots of conclusions that look and sound like this. So I want to go through another example here. I'm going to do this one way faster than I did the previous one because I'm going to talk about parts less. I just want to talk through another one, and then we'll call it a day here. Um, so same kind of deal. We're gonna really follow this very, very similarly to our previous one, but I'm just going to kind of work through a lot of these parts quite a bit quicker here. So this scenario, a hypothetical scenario, occurs in the future post-COVID. So I'm kind of picturing this being like next fall. Confident enough to reject the null p-value less than alpha value. Use that one test to assume could be some error in the testing. I need at least another test depending on the same size. Yeah, Claire. So you're kind of getting at a bunch of the important questions to ask here, which is, another question is like, if I set my alpha value at like 0.05, what happens if I get a p-value of 0.05 or something super close to that? I definitely agree with you that there's this issue of saying that maybe one of our conclusions should be, therefore, we need to do more research because we're sort of on the fence about it right here. We're kind of trying to make the best decision we can with just the data that's been collected right here. And we always want to be wary of overstating our conclusions, trying not to state too much. And so here we really are saying, like, we're going to continue believing the initially stated value unless we have solid evidence against that. Is kind of how I think about this here. Our default assumption is always the null hypothesis, and we're always saying we're thinking that maybe we can use this data to show that the null hypothesis is false, but we're always just looking at a chance, right? And as we discussed last week, we could be wrong in our decision. We could be incorrect that human body temperature is actually less than 98.6, and maybe we made the wrong call. But relative to our data, we did make the right call. Our data just does not like prove to us that null hypothesis value is false. Unfortunately, in statistics, you're never going to prove a statement true or false. You are just going to find that certain statements are wildly unlikely and other ones are pretty likely. Here we found that our statement that 98.6 is true was not too unlikely. Our statistics did not show a significant departure from that truth right there, and so we're going to stick it out with our original case. And again, you're asking the right questions here. What parameters are going to affect this here? Does it depend on sample size? And the answer is very much yes. And the other thing you should think is like if you sample like 10,000 people for anything, then it's almost certainly the case that the average that you're getting is going to be super close to the true population average. As your population gets huge, as your sample gets huge, then you are going to get a normal distribution that is shaped like all vertical and has like nothing in the tails out here, meaning all of your probability is going to be packed up right near the alleged population average. And if you see any sort of deviation in a sample of like 10,000 people, then right away you're going to be like, yep, no way the null hypothesis is true because we have so many people in our sample that we can be much more confident that our sample is a true reflection of the population overall. With very small samples, we would need to see a much more extreme result. Our X bar would need to be more crazy if we saw a very small sample right there, because with so few people, we don't want to let that inform our decision about the population as a whole unless we saw a really crazy sample from a small group right here. And again, we're going to talk through some scenarios tomorrow where I'm going to change a bunch more of these parameters a bunch more so that we can see the impacts of those parameters being changed right there. So, scenario 2 for the day here. We're going to look at a hypothetical future scenario. I'm sort of envisioning next fall semester when hopefully everything is all back in place and in person here. So let's suppose that a gym coach has identified you're cool in Listed Galaxy. Yeah, I do want to talk about these questions that you guys have here. Is having a large amount of people not too far away from an expected value compared to a dramatic result exchange with sample population relatively equivalent? Yeah, so you're totally right. So what your question asking there are we going to find that having a large sample but a small distance between the sample average and the population average, could that be comparable to having a small sample but a large distance from the proposed average? And yeah, that's kind of exactly what we're saying here. We have all these parameters that are all going to ultimately influence where that z-score value lived on our table. And it's totally the case that if we're sampling a small group, we need to see more deviation because it's only being measured out of a small group. If we're measuring a huge group, then just a little bit of deviation from the average is evidence that the average is wrong, because a huge group is not going to all deviate collectively above or below the true average very easily. So it's definitely the case that you might see a tiny difference in X bar and mu, but if your N is like 1,000,000, then that still might be sufficient to get you over the threshold of the P versus alpha. On the other hand, if your X bar if your sample size is very, very small, then we're going to need to see a very big X bar minus mu to get our z-score further off to the side to get that big enough to cross that p-value threshold with the alpha right there. And you are correct right there in Listed Galaxy. I like your final comment there. Sorry if this is worded awkwardly. Get used to wording things awkwardly. It gets difficult to verbalize these things even if you truly do understand what's going on. And so I'm going to just say right now, I would strongly encourage you guys to say phrases out loud to yourself, even if it makes you feel like a crazy person doing your homework in your bedroom or whatever you're doing. Say some of these sentences to yourself out loud, and it will help you to realize that some things you maybe think sounded crazy don't sound as crazy. And on the other hand, it might help you to be like, wow, that sentence didn't even make any sense at all, and kind of help you to like rephrase these things. There is going to be a lot of difficult verbalization coming up here, and I expect me to phrase some things weird and for you guys to phrase some questions weird. So good questions out there. All of those are exactly the things that we're going to be exploring in tomorrow's video and in next week coming up right here. So very good questions there. So our post-COVID situation here, I'm going to cruise through this guy so our video doesn't get on too long right here. We're going to say that this scenario is happening 1 year in the future right now. We're all back in school, and this coach is wondering, have kids' average mile times changed? That's the question that's being asked right here. So we've been given information about the original mile times and their standard deviations. We were given a sample size. we were given a sample average from the sample size after returning. And notice in this problem, I am also telling you a level of significance from which we can compare our p-value against. So it's much more typical to be given this in the problem like this. Determine at the alpha equal 0.05 level of significance. Is the coach justified in claiming that the average time has changed for these eighth graders? What we can clearly see is that the average mile time right here is different, or the sample average is different than the previous population average. But it could just be due to small variability in things that can happen, right? Two kids ate too big of a lunch that day, their times went up a little bit. Maybe that's all that happened right there. We know that there is a difference. What we don't know is that difference statistically significant? Is it actually meaningful? Is it actually truly representing a change? Or is it just representing a little bit of wobbles that happen out there when you collect a sample, right? So is the sample average different than the proposed population average? Yes. Does this show that the average time has changed? Not necessarily, right? Maybe this is just part of the natural variation of each individual runner out there. How can we attempt to prove that this does suggest this? Find the probability. I'm going to state this as find the probability that our average time is not, let's say here, let's find the average time that our probability is less than 9 minutes, 15 seconds. I'm going to say here less than or greater than is kind of what this should be because we're just looking for a difference right here. Let's find this probability that we see something that's that, oh wait, oh man, now I botched this, hold on. Okay, what this should have been, I'll just get rid of my dumb symbol right there. Find the probability that x bar is less than or greater than the 9 minutes and 36 seconds, assuming 9 minutes, 15 seconds is actually what the population average is going to be. So we're going to find this probability. We're going to find exactly how rare it was to see this sample. And if it's very rare that we would see the sample that we saw, 9 minutes and 15 seconds, then we'll go ahead and say there must have been a change. If it's not very unusual for us to get this 9 minutes and 15 seconds under the assumption, or sorry, if it's not that unusual for us to get the 9 minutes, 36 seconds under the assumption that 9 minutes and 15 seconds is average, then we'll go ahead and stick with that original answer right there. So let's go ahead and do our same steps right here, but we'll get through them a little bit quicker here. Let's determine how rare it would be to sample 45 people and get an average of 9 minutes and 36 seconds under the assumption that 9 minutes and 15 seconds is true, right? This part that I have in italics right there is so important. Every hypothesis test is done under the assumption that the null hypothesis is true. We're assuming it's true. If it leads us to a crazy place, then we'll say the reason we're in a crazy place is because the null hypothesis misled us. Right? That's how we reject the null hypothesis. We assume it's true even if we think it's wrong, so that if it takes us to a crazy, unlikely place, that's our evidence to go back and reject it. Right? So in this case, what were we given? We were given a population parameter of an average of 9 minutes and 15 seconds. Unfortunately, this is not a good format for me to see this number. I just want like one decimal that I can average right here. So notice that 15 seconds is a quarter of a minute. So I'm going to write this as 9.25 minutes. So our standard deviation here was 40 seconds. And so 40 seconds, that's 2/3 of a minute. And that's going to be 0.66. I'm just going to drag a couple decimal places out there. There's 2/3 the decimal right there. So I just need to get all these into a common measurement setting right here. So let's go ahead and state our hypotheses now. So in any good science, our hypotheses come first, collecting our sample comes second. Our hypotheses in this case, we're always going to form a null and an alternative hypothesis. Our null statement is always the statement of no change. Here we're debating about an average runtime. Our null hypothesis will always get an equals to sign. We are always assuming that our original information here is true. That's our 9.25 minutes. That's our 9 minutes and 15 seconds. Our alternative hypothesis is, and if you read the problem over here, we want to decide if there is a change. right? Just some amount of change is all we're saying. Just is there a change or not? So this means he doesn't think it's necessarily greater than or less than. He just thinks it's not equal to the 9.25 minutes. And what that means to me is that this is going to be a two-tailed test because we are okay with there being probability in either tails as far as an extreme results go. So what sample statistics were given to us? Well, in this case here, I see that we were given an N sample size of 45. We found an X bar, our sample average was 9 minutes and 36 seconds. Now 36 out of 60 is the same thing as 6 out of 10 if you divide both sides by 6, that's 0.6. So this should be 9.6 minutes. So we're comparing our sample of 9.6, sample average of 9.6, to our alleged population average of 9.25. So let's go ahead and fill out our distributions. We'll put all our stuff in Excel and we'll compute some things here. We were given this underlying distribution of 9.25 minutes with a standard deviation of 0.667 minutes. We then found of more interest to us, how are our samples distributed? How are our sample averages distributed? Well, because we had more than 45 students, I don't even care if that was normal or not. Since we had a sample size of more than 30, our sample average of the sample distribution will be normal. It's going to have the same average as the underlying distribution, but our sample standard deviation now, our standard error, is now going to be a little bit smaller here. We're going to divide by the square root of the sample size. And this is going to give us, we're going to now pop over into Excel because we now want to start making our computations happen here. So this is going to give me that X bar is really distributed according to the normal distribution. That decimal, oh wait, no, 9.25 is right. I was like 90 point, I think it's still my temperatures, 9.25. And we'll go to Excel for this guy over here. So let's start filling out our information that we've, oh man, not this again. I don't know why I'm not in typing mode. Draw, select. Is this not? Okay, no typing allowed. I guess I just have to scroll. So let's go ahead and fill out Excel with all of our information here. I've got a mu is me. Is it not? So am I locked out of writing mode now? I don't want to zoom in or out anymore. I just want to write things. I don't want to change any headers. Oh my gosh. I'm not drawing right now. There's no drawing going on. What did I do? Oh my gosh. Don't know how this happens. Okay, well, I'm back. Okay, let's see if it's okay over here. Hey, okay, we're underlined apparently. Mu, okay, now we're back. 9.25. We've got our sigma. It's 0.666666. Okay, I'm going to be smart here and just do equals 2 divided by 3. That's 0.67 right there. We've been given our sample size, it's 45. We've been given our X bar, our sample average is 9.6. We can compute our standard error that we need for our sample distribution. That's the point we're looking at right here. So I'm going to say this is equal to C14, our sigma, divided by the square root of n, C15. That's going to tell me that we're looking at almost a 0.1 right there, really close to 0.1, 0.0993. 0.099, and I'll just call it 38 to drag a bunch of those decimals out there. You need to be really cautious of over-rounding, by the way. Do not over-round. If you're not sure, you should be keeping a ton of decimals in these cases. Especially the smaller your numbers get, the more value all of their decimal places have out there. Do not be over-rounding here. So our test statistic, again, here a z-score, although we're going to get different test statistics later. We're still looking at this z distribution. I'm going to draw my graph here, my really bad graph right there. Um, all right, so what I don't know is how many standard deviations away from normal we are, but we can go ahead and compute that. Again, this should be our z equals x bar minus mu over sigma over root n. In this case, that's going to be our 9.6 minus 9.25 over 0.09938. And we're going to end up finding that our z value then is, I'm going to come over to Excel and do this, z score. I did it two ways last time. I'm just going to do it the easy way this time. Oh, wait, no. Sorry, that was the p-value did two ways. I'm going to do this the only way. Equals, it should be our x bar, that's C16, minus mu, that's C13, all divided by the standard error. That for me is C17. And this is going to tell me that this is about 3.5 standard deviations away from the null hypothesized average. That's pretty far. This is a pretty extreme result if the null hypothesis were true right there. If the null hypothesis is true, then the sample that we just collected is a little more than 3.5 standard deviations away from average. That's pretty extreme out here. So what we're looking at right here right now is that this is our z value right here, and that our p-value is just this little shaded region out here. Right? Our p-value is a very tiny shaded region. We're expecting to see a really small p-value. We're saying, what's the probability that if we were to do this experiment again, assuming the null hypothesis is still true, and to see an observation like this, what's the probability that you're going to see something more extreme than 3.5218? Very, very small. But I do want to point out real quick, one technicality associated with this is important. Notice our alternative hypothesis. Our alternative hypothesis always tells us what to do in our diagram out here. Although I guess, hang on, I'm getting a smidge ahead of myself right here. What I want to say here, I'm going to come down to our next kind of chunk right here. Our alternative hypothesis was that this is just going to be different than the 9.15. This says to us, we want area in both tails. Because we weren't suspicious that it was greater than or less than. We were just suspicious it was different. So we got like a 3.5, right? So we should be sitting right here and collecting that area. And we should be, no, this is a false, not quite a symmetric graph right here. But our p-value is the total area right? This has the cutoff located right here at our z equals 3.5218. And therefore over here, since this is symmetric, this should be z equals negative 3.5218 as our cutoff location right over here. All right. So what I'm interested in is finding that total amount of area out here. All right. We want to find this, and this is the probability that we'll see something at least this extreme, because as extreme means 3.5 standard deviations away or more. And since we didn't have a sidedness implied in this, we're getting either side, because this was just different than, right? It could have been that everybody came back from break faster instead of slower, and we still would have been drawing the same conclusions right here. So let's go ahead and compute this p-value now with these guys over here. To compute my p-value, what I can see is, and what I'm going to do is I'm going to call this my left tail. The left tail of my p-value, that's just one of my two tails. This should be, and I'm choosing left tail, by the way, because this has area to the left of a known location right there. So it's always easier for me to compute my left tail. So I'm going to say is equal to norm.s.dist because I do have standard normal stuff. I'm talking about z things. What is my z-score? It is the negative of, what did I do for my, okay, that's fine. It's the negative of my z-score. It's negative of C18, right? Notice here I'm sticking this negative on because I want the area to the left of negative 3.5218 or the area to the right of positive 3.5218, but they should be equal, so I'm just doing the one that's slightly easier for me. And what I'm finding, oh, too few arguments. That's right, I forgot my statement of true in here. And then I stuck one too many parentheses on and it fixed for me. All right, so there's my left tail area. So now I can get both tails by just saying this is equal to 2 times one of the tails areas. So I'll do times C19. And now we have both tails area right here for my p-value. So I'm going to say that our p-value here is equal to 2 times the probability that z is less than negative 3.5218. And that I'm getting from Excel that is 0.000428662. So how do we interpret this? Does this represent a rare event? Yes. Our p-value of p-value equals 0.000428662. Says there's only a 0.042 whatever 9% chance of seeing results this extreme. If, huge if right there, I can't bold it and underline it enough, if the null hypothesis were true. This is so unlikely that we think that the null must be false. All right, so we have computed the probability of seeing an event like the one that we saw occurring again if the null hypothesis were true. If the null hypothesis were true, then that would say to us that this is about a 0.04% chance of occurring. That's really, really rare. It's very rare to draw a sample like this. So either this gym coach just got a really rare sample that day, a wildly rare sample, a 4 in 1,000 sample, or the null hypothesis was wrong. Which one of those do you think is more appropriate in this scenario? Do you think that he just happened to get a 4 in 1,000 scenario? Or do you think that the null hypothesis is wrong and that children are actually running their mile times differently than they were before? I think it's wildly unlikely that we would have just drawn that very rare sample out of just that one sample right there. And so instead of continuing to believe the null hypothesis and just thinking we got a weird sample, I'm going to say I don't think that sample should be considered that weird. I think the null hypothesis is just wrong. Notice here our p-value is much less than our alpha value. And so I'm going to type out a conclusion here and we will call it a day. At the alpha equals 0.05 level of significance, our data were statistically significant, right? Not only did we see a difference between our sample average and our population average, but we decided that it meant something. We decided that it was so unlikely. It crossed our weirdness threshold of a 5% event with a 0.04% event. It was like more than 10 times more unlikely than our weirdness threshold. It definitely crossed the line. The p-value equals 0.000429. So we choose to reject the null hypothesis and conclude that 8th graders' average mile time has in fact changed Now, one thing we want to very much caution against right here is overstating what we know. Notice that we are only trying to choose between the null and the alternative hypothesis. The alternative hypothesis does not say that students got slower. It says that they got different. And therefore, that's the only conclusion that you are allowed to draw from our conclusion down here. So it would be incorrect here notice that we are rejecting the null in favor of the alternative. We are not claiming that run times got slower. We are claiming that they are now different. Notice that if we would have claimed slower instead of different, that would have affected our alternative hypothesis. And if our alternative hypothesis changes, then that changes the tails in which we're accumulating our area for our p-value. So our p-value changes if our alternative hypothesis changes. So our alternative hypothesis is what guides us on which tails we're accumulating area in for our p-value. And so it matters that we don't make conclusions that don't match our alternative hypothesis here, right? So even though it probably feels to you like the fact that our runners got slower because their mile times got longer, we are not making a claim about the sample. We are only making a claim about whether or not H naught was true. Here we said H naught isn't true because this sample would be wildly unlikely if it were, and so therefore H naught or HA is true. The average runtime is different than 9.15, and that's the only thing that we can really get away with claiming right here. If we wanted, we could change our hypotheses, perhaps perform a second test that's only a one-tailed test, then we could claim that average run times are now longer than they were before, but that's not what we set ourselves up to do here. So make sure that you're paying attention to your alternative hypothesis. It does influence the math that we end up doing at the later stages of our hypothesis test. So we did 2 full hypothesis tests here today. We dragged them out a little bit, but one of the really important things that we did is we tracked all of our information here in Excel so that we could handle these things a little bit more easily. If you do these in Excel and you're always referencing other cells' information, then it makes it really easy for us to maybe modify this and play around with things a little bit. We're going to do a bit more of that next class. Next class, rather than just doing a couple examples, we're going to break one example down and say, what if they sampled 40, 50, or 60 people and got this result? What if they sampled 40 people and got these 3 different averages? So we can kind of see how the numbers will affect the p-values that we're going to end up getting at the end of the day out there. So more examples tomorrow. And also importantly, 2 new scenarios in the next video. In this scenario, we kept on talking about averages and we kept on knowing the standard deviation. But the thing that you should be asking yourself right now is, how is it that we're calling a population average into question, but not also calling the population standard deviation into question? How would we know one of those without knowing the other? The other thing that we get to talk about in the next video is proportions rather than just averages. So we're going to come back to getting some information from our binomial distribution about proportions as well, and folding that into the same concept right here. So I'm going to go ahead and wrap it up for the day here for this video. Next video, we're going to get a whole bunch more examples and really looking at 3 different hypothesis tests. The z-test for single means with the standard deviation known, a t-test for a single mean when the standard deviation is not known, and a p-test or a proportion test for when we're testing for a proportion rather than testing for an average like we did in our 2 examples here today. So that wraps it up for me today. Thanks for the questions in chat over there, guys. Those were good. And I will see you for our next video here tomorrow. Have a good one, everybody.